Okay, so greetings everyone. One more time, thank you for joining this webinar, The Truth About ZFS. My name is Oris and I'm a solution engineer here at StarWind. So welcome everyone. So before we actually start, let's just make a short recap on our today's agenda. So we'll start by talking a bit about the ZFS and its actual benefits, what you can take from it. After that, we're gonna also mention, to be completely fair, just as well, its drawbacks. And then we will see why the ZFS is not yet implemented in VMware and Hyper-V. After that, I'm also going to show how ZFS is delivered, namely ZFS on Ubuntu, and not just on the Ubuntu, but that will be on the example of our StarWind, SAN, and NES. And of course, as traditionally, at the end of the webinar, we're going to have a short questions and answer session where you can ask any of your questions and I'll also try to answer them. So let's actually move forward. So speaking of the ZFS benefits, now we previously covered this in our past webinars, but let's just make a recap. So first of all, it's been designed for almost infinite scaling. No doubt about that. We can already see it clearly from its name. So zettabyte file system. Now, the benefit, in fact, about the ZFS is most likely the hugest benefit, is that it's not just the ordinary file system, but it's also the volume manager. So you practically get an all-in-one solution with ZFS. You don't really need other tools to work with your storage. So ZFS alone is enough to create a file system, combine your disks with adding resiliency, and manage your ZFS datasets to provide them as block storage or NFS or SMB shares. While additionally, RAID Z allows providing the required redundancy for data with various RAID Z levels configurations according to your requirements. Moreover, ZFS is all about data integrity, data consistency, and overall about keeping your data safe and clean. So, as we already know, ZFS is transactional copy and write file system, meaning it does not overwrite data in place, but creates new blocks instead, so the original data remains intact. Then the pointers are updated to look at the new block location rather than the old. And finally, only once the Uber block is updated to point to new data, the old data is deleted to free up storage space. And therefore, we are not afraid of corrupting data during power outage, for example. And in combination with checksumming and verifying the checksum when data is read, ZFS also ensures data integrity. Now, as to other features that ZFS gives us, well, the first one to mention are the snapshots. So basically, the first class read-only snapshot of the file system. It is mirrored copy of the state of the file system at the time the snapshot was taken. So speaking of ZFS, you can keep up to 2 to 64 snapshots in your pool. So ZFS snapshots are persistent across reboots and they don't require any additional backend store. They use the same storage pool as the rest of your data. And basically, a ZFS snapshot is a copy of the Merkle tree in that state, except we make sure that the snapshot of the Merkle tree is never modified. Now, the other cool feature about ZFS is definitely compression. So just a few words on it. It is transparent, so inline if you enable it, and it is enabled and disabled as per dataset or volume. Obviously, compression can vary on the disk space savings. So if the dataset is storing mostly uncompressed data, such as plain text, log files, or configuration files, the compression ratios can be massive. If the dataset is storing mostly compressed images and video, then you most likely won't see much, if anything, in the way of space savings. Now, The other feature I wanted to mention behind ZFS is the deduplication. ZFS uses block deduplication only, so block deduplication shows all the same blocks in the file minus the blocks that are different. So this allows storing only the unique blocks on disk and reference the shared blocks in RAM. So it's more efficient than byte deduplication and more flexible than file deduplication. However, it has its drawbacks, and these I'm going to mention as part of our next part of today's webinar. So actually, ZFS and the drawbacks behind it. Now, speaking honestly, talking about ZFS drawbacks, I would actually mention them as the peculiarities and nuances of operation, and in most cases, these drawbacks can be overcome. So the first and foremost drawback, personally for me, when we are talking about ZFS, is its scaling options. Now, basically what I mean is that RAID Z cannot be scaled by simply throwing in another drive to your VDEV. So instead, ZFS scales by adding new VDEVs to the pool. Therefore, for example, if you have RAID Z2 with 2 parity drives, you would need to add at least 4 more drives so that the new VDEV had the same failure sustainability, basically the same resilience level. Otherwise, if you add a single drive VDEV, which is of course possible, it will basically become a single point of failure for the entire pool. But to tackle this, what is actually currently required is the proper and thorough planning for storage capacity. Of course, as for scaling, there is an option to replace the drives with the larger size and one by one up till you get all of them to the larger capacity. And in the next ZFS, next OpenZFS release, I guess we are all also waiting for the ability to actually easily scale VDEVs by adding more drives in the RAID Z. Now, the next thing I already mentioned is the actual, well, the duplication drawbacks. The duplications store the deduplication table in RAM, and in case it will not fit, meaning if the RAM amount will not be enough, it will start accessing it directly from the storage, which will result in dramatic performance decrease. So either a ton of RAM or instead compression might be a better alternative if we are talking about the storage savings. Now, the other thing I also want to mention is regarding the performance of the device, and namely write performance. So the first thing we need to know is that ZFS uses transaction groups. Well, as the name implies, groups of transactions that act on persistent state. So there are two types of writes, asynchronous and synchronous. So with asynchronous writes, everything is quite simple. They group together in a transaction group in RAM and then are written to persistent storage. With synchronous writes, the situation is a bit different, as an application, for example, requires acknowledgement the data has been written to the persistent storage. Synchronous writes are correspondingly safer because the client system waits for the acknowledgement before it continues on. The price of this safety is often performance, especially when writing to slow arrays of hard drives, as by default, ZFS intent log is created as part of the same and of the main pool. Now, we need to understand also that all writes, including synchronous and asynchronous writes, are aggregated in RAM and committed to the pool in transaction groups. The difference with sync writes is that they're also written to a special area of the pool I mentioned as ZIL, so ZFS intent log, in parallel with writing them to the aggregation in RAM. Now, this doesn't mean that the sync writes are actually committed to main storage immediately. It just means that they're buffered on disk in a way that will survive power outage, for example. In normal operation, blocks written to ZIL are never read from, and the sync writes still get committed to the main pool in the transaction group from the RAM alongside the asynchronous writes. Now, that synchronous part essentially is how you can be sure that an operation is completed and the write is safe on persistent storage instead of cached in volatile memory. So during the import process of a Z-pool, ZFS checks the intent log for any dirty writes. If it finds some, for example, again, after the power outage, it will replay them from the ZIL, aggregating them into the transaction groups and committing the transaction group to the pool as usually. So simply put, ZFS intent log being part of the main pool results pretty much in double writes, since they goes to disks once for ZIL and then to the main pool as part of the transaction group. This is specifically painful for small random writes, and as a result, we fight for the throughput and IOPS, decreasing the overall performance. So if your system experiences a lot of synchronous write operations, a secondary log device or simply slog can help. So the slog is a special standalone VDEV that takes the place of the ZIL. It performs exactly like ZIL. It just is placed on a separate isolated device, which means that double writes due to synchronous operations don't consume the IOPS or throughput of the main storage itself. And again, the only time the slog gets read from is after a crash, just like the ZIL. However, we also need to understand that the slog's primary function is not the actual performance boost, but to save data that would otherwise be lost in the event of power failure. So for mission-critical applications, it could potentially be quite costly to lose the 5 seconds of data that would have been sent over in the next transaction group. And that's also why slog isn't truly a cache. It's actually a log like its name suggests, and is only accessed in the event of the unexpected power failure. So the best recommendation here is for the system with multiple synchronous writes is to use the separate slog on the fast and durable flash storage to avoid the double write operations. So now let's actually try to understand why ZFS is missing in the Hyper-V and VMware pretty much in what we call the industry standard hypervisors. Well, there are several reasons for that. So the first thing is that ZFS has been initially designed not just a file system, but also as a volume manager to handle storage pools instead of just presenting a file system that could be easily used for cluster storage. So again, it's mostly focused on the single or multiple pools and the management. And if we are talking about the world of virtualization, both VMware vSphere and Microsoft Hyper-V operate in most of the cases, although not exclusively, as clustered environments with shared storage. The next thing is that it's fair to say that ZFS has been built around the HDD technology, around the spinners, and optimized for operation with spindle drives. Well, definitely, ZFS can very well work with SSDs, but its peculiarities might not deliver the best SSD performance you might expect, especially on small random writes. And here comes the other thing. While ZFS is no doubt a great choice for backups, archival, file, and media storage, where a typical workload is large sequential writes, it's not the best case when it comes to virtualization. The thing is that virtualization workloads are typically small random writes. With this, we hit the ZFS fragmentation issue, which decreases the performance. And two parts basically come into play here. So ZFS does not rewrite data in place, as we know. Instead, it writes to new or free blocks and then frees up the old ones. So with large blocks on sequential workload, this is not a huge issue, but with small random blocks, it is, as it increases the fragmentation. So when ZFS pool gets almost full, it will start using freed up blocks and will require more time to find those small chunks of free space and perform the write. Plus, also this will result in slower reads as data gets more fragmented. The second part is also related to the ZIL, as I mentioned earlier. So even heavier fragmentation occurs when a lot of small random transactions are created and temporarily written to ZIL, which is part of the main pool, and then deleted. So after an amount of time running this way, it comes to a point that the ZIL could not allocate sequential blocks for its transaction entries. And once the ZIL transactions are deleted, fragmentation occurs. So every ZIL transaction that is allocated and then freed on disk basically causes gap to appear between ZIL's entries and pool's data. Plus, you correspondingly have ZIL transaction competing for throughput with other I/O occurring at the same time. However, we already know the fix for that, so slog on the separate, fast, and durable storage is intended also to overcome this issue. And now, to be completely fair, if we are talking about the fragmentation, all of this doesn't occur straight away, but mostly, and depending on the workload, when the pool gets 96% full, if we are talking about the latest ZFS releases. So previously, it was 80% of the full. Most likely over the web, you can find articles saying that it's still 80%. But the important thing here is that ZFS allocates block using space maps. And there are multiple of those. So when a space map is more than 96% full, so again 80% for all builds, ZFS will switch from first fit to best fit allocator. And again, so this is a per space map decision. You can have an 80% full pool with some space maps well over that value and maybe already at over 96%. So when writing to such space maps, ZFS will start using the slower best fit allocator. And of course, the honest way to mention this is that ZFS usage depends on your workload requirements. Pretty much, if we are talking about the world of virtualization, everything depends on your needs in speed, in write, and in read operations. However, taking overall of the mentioned above, ZFS is not the best fit for exactly virtualization workloads. Now, also to show you how ZFS is delivered inside of ZFS on Ubuntu, I'm going to use our StarWind ZNS. So what we have here is the ZNS virtual appliance. All the features, detailed metrics, and functions of it will be covered in one of our upcoming webinars. But if we will go to the storage tab, we will see that we have a set of drives fed through to it, and some of our drives are already used for ZFS. Some of them are also used for the MDADM, which is also part of the functionality of the StarWind ZNS. And if we go to our pools, we will see that we have one RAID Z2 and just one mirror pool. If we go to the settings, we'll be easily able to see the layout details and the number of drives in the Z pool. Now, to access the internal of the StarWind ZNS, I'm just going to use the SSH connection. And pretty much it will be no different from the common ZFS on Ubuntu. So in ZFS on Ubuntu, well, ZFS is already the ZFS module is already delivered with the kernel. So pretty much what we just need to do is install the ZFS tools. Of course, if we are talking about the StarWind NAS, these are already installed and come readily available. So pretty much there are no other operations required. In the common ZFS on Ubuntu, the only thing you'll need is just to get the ZFS tools installed and you'll be ready to create the RAID Z and your VDEVs and the Z pool. So if we check the ZFS version right here, we will see it's currently running the default 0.8.3 release, which is supplied with the Ubuntu 20.0.1 by default. There are other available, the more recent versions of ZFS available, such as 2.0 with 2.1 already coming to Ubuntu. In StarWind NAS, we are currently running on 0.8.3 and will be upgrading it as part of the appliance to the newer releases. And of course, ZFS is always ZFS, so the commands we use and the operation with it just is the same pretty much almost as in any other Linux distributive. So we can just check the Z pool status and we'll see our two pools, RAID Z2 online and the other one just the mirror pool. Now at this point we are actually getting to our question section. So if anyone has any questions regarding our today's webinar, I'll be more than happy to answer them. So please ask those in the questions section. Okay, so it seems there are no questions. Just to let you know, the record of this webinar will be available on our website. Oh, and I have one question from the Jason Clark. So how does the performance of ZFS compare to traditional RAID for general storage, such as the NAS? From my experience, ZFS performance for file storage, backup, and media storage overall is just very well compared to the traditional RAID setup. So I cannot tell that there is the significant performance difference. For traditional workloads, again, such as file service, it delivers the great performance. And let's just have a couple of minutes. Perhaps someone else will also have other questions. Okay, and it seems that there are no more. So I would like to thank everyone for joining this webinar and for finding your time to actually attend it, and wish everyone to have the good rest of the week and stay safe. Goodbye.